Right now, there's a plan on the table to send human beings to Mars. But nobody is telling you what that ticket actually costs, or what happens to your body the moment you arrive. Mars is not just a red dot in the night sky. It is a world with mountains taller than anything on Earth, storms that last for months, and a past that scientists say once looked a lot like home. In this video, we're going to take you there, the science, the survival odds, and the real price tag of making Mars humanity's second address. If you want to know what no space agency puts in the headlines, hit subscribe. This channel is where the real numbers live. 4.5 billion years ago, the solar system was not a neighborhood. It was a war zone. Clouds of gas and dust spun violently around a young sun, colliding, merging, tearing apart, and starting over. Out of that chaos, a small rocky world began to take shape in a zone close enough to the sun to stay warm, but far enough to avoid being swallowed by its fire. That world was Mars. And in its earliest days, it was nothing like the frozen, rust-colored desert we see today. It was wet. It was warm. It had a sky. Scientists at the National Aeronautics and Space Administration and research institutions across the world have spent decades studying the surface of Mars from orbit, from the ground, and through the lens of meteorites that broke away from the planet billions of years ago and somehow found their way to Earth. What they have pieced together is a story that reads like a tragedy. Mars once had everything: a thick atmosphere, liquid water flowing across its surface in rivers and lakes, volcanic activity generating heat from within, a magnetic field wrapping around the planet like a protective shell. For hundreds of millions of years, the conditions on Mars may have been close enough to those on early Earth that the same chemical reactions that led to life here could have been happening there too. Then something went wrong. The core of Mars cooled. When a planet's core goes cold, the magnetic field weakens and eventually collapses. And when the magnetic field disappears, there is nothing left to protect the atmosphere from the solar wind. A constant stream of charged particles blasting outward from the sun at hundreds of miles per second. Over millions of years, the solar wind stripped Mars of its atmosphere molecule by molecule. The air thinned. The planet cooled. The water froze or evaporated into space. And Mars became what it is today, a silent, frozen world with an atmosphere so thin it would kill you in seconds if you stepped outside without protection. The atmosphere on Mars today is composed of roughly 95% carbon dioxide, with small amounts of nitrogen and argon. The atmospheric pressure at the surface is less than 1% of what we experience on Earth. To put that in human terms, stepping onto the surface of Mars without a pressurized suit would be like being exposed to the vacuum of space. Your blood would begin to boil, not from heat, but from the drop in pressure causing dissolved gases to come out of solution inside your body. You would lose consciousness within about 15 seconds. You would be dead within 2 minutes. Not from cold, not from radiation, simply from the air, or rather, from the complete absence of it in any form your lungs could use. And about temperature, this is where Mars surprises people. There's a common image of Mars as just a cold place, like Antarctica, but in space. The reality is far more extreme and far more unstable. The average surface temperature on Mars is around -80 degrees Fahrenheit, which is approximately -62 degrees Celsius. But that average hides a violent range. Near the equator on a summer afternoon, temperatures can briefly climb to around 70 degrees Fahrenheit, roughly 21 degrees Celsius. That sounds survivable. That sounds almost pleasant. But then the sun sets, and within hours, the same spot drops to -195 degrees Fahrenheit, which is approximately -125 degrees Celsius. In one Martian day, you can experience a temperature swing that would shatter unprotected metal, crack exposed rubber seals, and overwhelm the thermal regulation systems of any habitat that was not specifically engineered to handle it. Space itself, the empty void between planets, is even colder. In the deep vacuum between Earth and Mars, temperatures can fall to around -455 degrees Fahrenheit, which is approximately -270 degrees Celsius. That is less than 3 degrees above absolute zero. the theoretical point at which all molecular motion stops. In a vacuum, the only mechanism for heat transfer is radiation. A spacecraft loses heat by radiating it outward, and in the absence of a heat source, that process ends only when all warmth is gone. The journey to Mars runs straight through that void for somewhere between 6 and 9 months. If a human crew left Earth today on the fastest available trajectory, they would spend roughly 7 months in that void before reaching Mars. 7 months in a pressurized capsule no larger than a modest apartment. 7 months exposed to radiation that no amount of shielding currently eliminates entirely. Once a spacecraft leaves Earth's magnetic field, protection ends. A Mars mission crew would receive radiation doses multiple times higher than astronauts on the International Space Station. The long-term cancer risk from a single round-trip Mars mission is estimated to increase a crew member's lifetime cancer mortality risk by somewhere between 3 and 5%. That is the current best estimate from researchers at the National Aeronautics and Space Administration and the European Space Agency. Then there is the question of the human body itself. In microgravity, bone density decreases at roughly 1 to 2% per month. Muscle mass deteriorates. The cardiovascular system weakens. Vision problems have been documented in a significant percentage of astronauts, caused by fluid shifting toward the head and increasing pressure around the optic nerves. By the time a crew arrived at Mars after 7 months in transit, they would be physically diminished. And then they would have to land on a planet and immediately begin surviving on a world whose gravity is 38% of Earth's, something the human body has never evolved to handle. The surface of Mars is not a blank wasteland. It is a specific kind of hostile. The largest volcano in the entire solar system is on Mars. Olympus Mons rises about 16 miles above the Martian surface, nearly 3 times the height of Mount Everest. The Valles Marineris Canyon system stretches approximately 2,500 miles across the surface, in places 4 miles deep. If it existed on Earth, it would stretch from the Atlantic coast to the Pacific coast of the continental United States. This is not a dead world. It is a world that burned itself out. Now, and this is the part of the Mars story that keeps scientists awake, there is water on Mars. Not flowing rivers, not open lakes, but water. The Martian polar ice caps contain enormous quantities of frozen water mixed with frozen carbon dioxide. Beneath the South Polar ice cap, radar data from the Mars Advanced Radar for Subsurface and Ionosphere sounding instrument aboard the European Space Agency's Mars Express orbiter detected what appears to be a subglacial lake, liquid water sitting beneath about 1 mile of ice. The debate is not about whether the radar signal is real. The debate is about what is causing it. Liquid water kept from freezing by salts, or a layer of conductive material mimicking that signature. The answer is not yet settled. What is not in debate is that water ice exists on and just below the surface at the poles and in mid-latitude regions. The Mars Reconnaissance Orbiter has photographed exposed water ice in fresh impact craters. The Phoenix lander confirmed water ice directly below the surface near the northern polar region. The Curiosity rover detected ancient lake beds and river channels in Gale Crater, features that could only have formed through sustained liquid water flow in Mars's deep past. The question of life on Mars is inseparable from the question of water. On Earth, wherever there is liquid water, there is life without exception. In volcanic vents miles below the ocean, in hypersaline lakes, in Antarctic ice, wherever liquid water exists in contact with chemistry and energy, biology has found a way. Scientists cannot rule out that the same might be true of Mars. Not on its surface today, which is sterilized by ultraviolet radiation, but potentially in protected subsurface environments where liquid water might persist. No Mars mission has yet returned a definitive positive result for life. The Viking landers in 1976 conducted experiments designed to detect biological activity in a Martian soil and produced results debated for decades. The current scientific consensus leans toward unusual chemistry over biology, but the debate has never fully closed. The Perseverance rover, which landed in Jezero crater in February 2021, has collected rock and soil samples sealed in titanium tubes, sitting right now on the surface of a crater that 4 billion years ago was a lake. Those samples are waiting for a return mission that has not yet launched. Experts in astrobiology are careful not to overclaim, but the scientific case for Mars as a potentially habitable world, not necessarily today, but in its past, and possibly in protected subsurface niches today, is taken seriously by the mainstream scientific community. It is not fringe speculation. It is the reason Mars receives more robotic missions than any other planet in the solar system. Now we arrive at the part of this story that nobody in any official space agency press release will give you in plain numbers. The real cost, not the inspiring version, the actual version. The most famous name in the Mars conversation today is Elon Musk, the founder and chief executive of Space Exploration Technologies Corporation, known as SpaceX. Musk has stated publicly and repeatedly that his goal is to make humanity a multi-planetary species, with Mars as the primary destination. He has described a vision of a self-sustaining city on Mars with a population of 1 million people. He has said that the cost of a ticket to Mars could eventually fall to around $100,000 per person, comparable, he argues, to the cost of buying a house in a major American city. The vehicle intended to accomplish this is called Starship, a fully reusable two-stage rocket system that, if it performs as designed, will be capable of carrying up to 100 metric tons of payload to Mars per launch. The SpaceX estimate for what it would take to establish a self-sustaining city on Mars is approximately $1 trillion over several decades. $1 trillion. That is a number that needs to be held against something real to feel its weight. The entire annual budget of the United States federal government for discretionary spending. The portion of the budget that Congress votes on each year covering defense, education, transportation, scientific research, and everything else outside mandatory programs is approximately $1.7 trillion. $1 trillion for a Mars city is roughly 60% of the entire discretionary federal budget of the United States for 1 year. It is more than the gross domestic product of most countries on Earth. But the $1 trillion figure is SpaceX's optimistic projection for the mature, efficient, scaled-up version of the program. After reusability has been perfected, after in-space fuel production has been demonstrated, after dozens of missions have refined the logistics, the early missions will cost vastly more per unit of payload delivered. The first crewed mission to Mars, which SpaceX has targeted for the late 2020s, though timelines have historically shifted, is estimated by independent analysts to cost somewhere between $5 billion and $10 billion for the mission alone, not counting the years of vehicle development and infrastructure that preceded. The National Aeronautics and Space Administration's own internal studies for a crewed Mars mission, conducted over many years as part of various architecture studies, have consistently produced estimates in the range of $400 billion to $500 billion for a full program capable of landing humans on Mars and returning them safely to Earth. That is roughly equivalent to the entire budget of the National Aeronautics and Space Administration for the next 50 years at current funding levels. The reason the cost is this staggering is physics. Getting mass off Earth and into space is extraordinarily expensive. A fully fueled Starship vehicle on the launch pad is roughly 90 to 95% propellant by mass. The payload is a tiny fraction of the total. Every kilogram delivered to the surface of Mars requires dozens of kilograms of propellant burned across multiple stages. This is the tyranny of the rocket equation, and no innovation in manufacturing changes the underlying physics. To support a crew of 6 people on Mars for 18 months, the minimum stay required to wait for the orbital alignment that makes the return journey efficient, you need approximately 30 metric tons of supplies. Food, water recycling systems, medical equipment, habitat components, power generation, spare parts, communication systems. 30 metric tons delivered to the surface of Mars represents a launch cost in the hundreds of millions of dollars before adding the vehicle, the mission operations team, the training program, and every other line item that goes into keeping human beings alive on another planet. The National Aeronautics and Space Administration estimates the cost of keeping a single astronaut on the International Space Station for 1 year at approximately $150 million. Mars is not a space station in low Earth orbit. The cost per person per year of early Mars survival would be an order of magnitude higher. Local resource utilization, the ability to make things on Mars from Martian materials, is the key to making Mars economically viable over time. The atmosphere is 95% carbon dioxide. Water ice exists in the soil. Combined with electrical power from solar panels or nuclear reactors, these raw materials can produce rocket propellant and breathable oxygen. The Mars Oxygen In Situ Resource Utilization Experiment instrument aboard the Perseverance rover already demonstrated this in April 2021, successfully converting Martian atmospheric carbon dioxide into oxygen. The amount produced was enough to sustain a human for approximately 10 minutes. Small, but real, and it happened on Mars. The single most honest thing that can be said about the cost of moving to Mars is this: the first people who go will not be paying customers. They will be explorers, people who accept extraordinary personal risk in service of a mission whose value is measured not in profit, but in the expansion of what humanity knows. The economics of Mars settlement lies decades, or possibly centuries beyond the first footprint. What we are buying with the first $1 trillion is the knowledge and infrastructure that makes the next trillion cost half as much. The return on that investment will never be monetary. It will be civilizational. Mars is waiting. It has been waiting for 4.5 billion years. The mountains are there. The frozen water is there. The ancient lake beds are there, holding whatever secrets they have kept through billions of years of silence. The question has never been whether Mars can be reached. The question has always been whether the human species is willing to pay, in money, in risk, in time, in lives, for the answer to the oldest question we have ever asked. Are we alone? Is there somewhere else we can go? Is the story of life bigger than one pale blue dot suspended in a sunbeam? The price tag is real. The challenge is real. And for the first time in the history of our species, the technology to attempt the answer is real too. Mars is not a destination in the way that a city or a country is a destination. It is a commitment that says the human story does not end here, does not end on this one fragile world where a single asteroid or a single degree of atmospheric change could rewrite everything. Every mission that has ever been sent to Mars, every rover, every lander, every orbiter, has been a sentence in a letter written by our species to the future, a letter that says we looked outward and we did not look away. The mountains of Mars have been waiting in silence longer than our sun has had planets circling it. What we do next is up to us. If this video changed the way you think about what is possible and what it actually costs to make it real, then this channel is exactly where you belong. Every week we go deeper into the science, the money, and the human story behind the greatest questions in space. Hit subscribe right now. Turn on notifications, because the next video is going to take you somewhere even further, and you do not want to miss where we are going.